everybody, welcome back to another video. This video is going to go through inverse functions and logarithms, mostly on the logarithm side of things. If you haven't seen our previous video on exponential functions, I recommend watching that first. I'll link it above. But otherwise, let's learn a little bit about logarithms, go through some review. So we're going to let a be larger than 0. And the way we define logarithms, so we say log base a of x is equal to y if and only if I raise a to the power of y and I get x. So when you're solving logarithms, so let's say I have log base a of x, well, whatever that number is, it's saying a to the power of that number y is equal to x. Now, one thing I want you to notice is that this looks like y equals a to the x, but with x and y swapped, right? And that's because logarithms and exponential functions are inverses of each other. So if I have y equals a to the x, maybe I'll call this, let's see, maybe I'll just do it like this. So from our previous video, we saw this goes, it has domain all real numbers and range 0 to infinity. And inverses kind of swap domain and range, right? So if I have y equals log base a of x, this is going to have domain 0 to infinity, and it's going to have range all real numbers. So this is super important. When we're taking logarithms, the domain is 0 to infinity. We exclude 0. Let's think about that though, right? So if, say we wanted to include 0, well, can I take some positive number a and raise it to an exponent, and can I ever get 0? The answer is going to be no, right? Because a to a power, it's just, multiples of a, or powers of a, sorry. And negative numbers as well, well, if a is larger than 0, well then multiplying a with itself a bunch of times, I'm not going to get a negative number. So that's one way you can kind of keep this straight. So we'll go to Desmos in just a sec so we can see some examples, but what I wanted to do is just to get comfortable with logarithms is, let's look at this here. So I'm saying log base 10 of 0.001. Well, 0.001 is 1 over 10 to the 3, right? Another way of writing that is 10 to the power of negative 3. So we're saying 10 to what number is equal to 0.001? Well, 10 to the negative 3. So again, this is the same as saying that 10 to the negative 3 is equal to 0.001. Now, like I mentioned, logarithms and exponentials, these are inverses of each other for the same base, right? So we need a and a. But let's look here. So log base a of a to the x, we're saying, well, a to what power is equal to a to the x? Well, x. So notice here, kind of, we can cancel the log a and the a. Similarly, if I have a to the log base a of x, well, log base a of x is a number where a to that power is equal to x. So we're raising a to that power, so we get x. Very good. Next thing I'll do is I'll go to Desmos, and then we'll kind of review some of, the rules, the algebraic properties. We'll do some practice with computation, solving equations, and then computing limits. But let's go to Desmos really quick. So I'll pause briefly and meet you over there. All right, everyone, welcome to Desmos. So you can see here I have 3 graphs going on. The red graph kind of in the bottom, this is log base 2 of x. Then I have the line y equals x, and then 2 to the x. So notice 2 to the x and log base 2 of x, these are inverses of each other. And we can see that by noticing you can reflect across the line y equals x and go from one to the other. Now, let's take a look at log base 2 of x. So this red graph here. As x goes to infinity, notice that the function goes to infinity as well. It just grows very slowly. So notice how long, look, I've zoomed way out, and it still hasn't even reached 1,000, versus the exponential, look how quickly it grows. So going to positive infinity, it also goes to infinity, just very slowly. Notice now as I go towards 0 from the right, so these are going to be things very close to 0, so 0.001, 0.000001. So if that's my x value, I'm saying 2 to what power gives me something close to 0? Well, these are going to be negative numbers, right? So that becomes 1 over 2 to a large number. So that's how I'm going to get to negative infinity. So, for studying purposes, keep this basic shape in mind, right? So as I approach 0 from the right, I'm going to go to negative infinity. As I approach infinity, positive infinity, I'm also going to go to infinity. Another thing I want to point out is notice, what is this point? So this is 1 comma 0, and that's because we're saying, well, 2 to what power is equal to 1? Well, 2 to the 0. All right, so I think, this is just the general visualization I want you to keep in mind. Maybe one other thing I'll say is similar to how when we looked at, like 1/2 to the x, notice how it's reflected across the y-axis. If I do log base 1/2 of x, notice now that it's flipped across the x-axis. So I haven't seen too many examples in our class where we're having kind of these bases that are between 0 and 1. I just wanted to show you kind of what this looks like. All right, very good. I'll meet you back at good notes so we can work through some examples. Alrighty, welcome back everyone. So what I want to do now is go over some algebraic properties. Oops, let me silence my phone. All right, so you can actually prove all of these by just remembering the corresponding properties of exponentiation, but log base a of x times y, this is going to be log base a of x plus log base b of y. Log base a of x over y is log base a of x minus log base a of y. And if I have log base a of x to the power of r, this becomes r log base a of x, and here r is any real number. So super important to keep in mind. These will make the upcoming problems much easier. So now we have some practice with, computing exact values of each of these expressions. So let's do log base 5 of 125. So this is saying if this is equal to y, this means that 5 to the power of y is equal to 125. But then that's 5 to what power? So 3 should be y. 5 to the 3 equals 125. All right, let's try this one. So I'm going to rewrite this as log base 3 of 27 to the negative 1. And using our logarithm rules, this is negative log base 3 to the 27. Well, 3 to the 27, or 3 to the what equals 27, that's 3. So this should be negative 3. And the way we can check this is we say, well, 3 to the negative 3 is 1 over 27, right? Very good. Part C, this is going to give us practice with using more of our logarithm rules. So let's do the subtraction first. This is going to be log base 2 of 6 over 15 plus log base 2 of 20. Now notice it's super important that these bases are all the same. So if these were different bases, you couldn't do this rule right away. You could use a change of base formula, which we haven't covered in this video, but you can let me know if you'd like to do that. But okay, 6 over 15, let's rewrite this as, let's divide by 3 and write this as 2/5. And then, so this is going to be log base 2 of 2/5 times 20. So 20 over 5 is 4. So this becomes log base 2 of 8. And well, 2 to the power of 3 is equal to 8. So the answer here is 3. Next one, all right, so we have e to the negative 2 ln of 5. I'm going to rewrite this as e to the ln of 5 to the negative 2. So that's using, again, one of our logarithm rules. So multiplication out front can become the exponent inside of the ln. One thing I'll point out here, ln means natural logarithm, and it means the base is the number e, so about 2.71. But now we know e and log base e are inverses of each other, so this is just going to be 5 to the negative 2. And let's do one more. So this will be more practice with using the fact that logarithms and exponents are inverses of each other. So let's take a look at the inside one first. So it's going to be ln of, now what I'm going to do is, ln is log base e, this becomes ln of e to the 10, which I can rewrite as 10 ln of e if I'd like, or I can just scratch out right away. But ln of e, that's saying, well, e to what power is equal to e? That's 1, so this is 10. Very good. Next thing I want to do is talk about how we can solve equations for x. So, this is going to be either taking logs of both sides or raising both sides to an appropriate power. So same way, if I have x squared equals blah, 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 I can take square root. So we have e to the 7 minus 4x is equal to 6. So I'm going to rewrite this as, I'm going to take ln of both sides. So ln of e to the 7 minus 4x is equal to ln of 6. Then on this side, e and ln, those are inverses. So what we're left with is 7 minus 4x is equal to ln of 6. And now I can solve for x, right? So we'll have negative 4x is equal to ln of 6 minus 7. And let's divide by negative 4 on both sides. So x equals, I'll put negative ln of 6 minus 7 all over 4. And you could plug this into a calculator or leave it like this. Very good. Let's try the next one. So we have ln of x squared minus 1 equals 3. What I'll do here is I'm going to raise both sides to the power, I'm going to do e to the power of both sides. So ln and e go to 1, so I have x squared minus 1 equals e cubed. So then x squared equals e cubed plus 1. So then x equals plus or minus root e cubed plus 1. And this looks good to me. All right, very good. And last one, we have 2 to the x minus 5 equals 3. So then let's take log base 2 on both sides. So log base 2 of 2 to the x minus 5 is equal to log base 2 of 3. So then we have x minus 5 equals log base 2 of 3. And this gives us x equals log base 2 of 3 plus 5. All right, very good. Last set of problems, I want us to think about limits. So, basic shape to keep in mind for when the base is greater than 1 is they're going to look something like this, right? And this is the point here, 0, 1. Or sorry, 1, 0. All right, very good. So we have here, so ln, that's base e. We're approaching 3 from the right and x squared minus 9. So these are values larger than 3. Notice that we need to do it from the right because if we went from the left, these would be values smaller than 3. So then subtracting 9 once we square, that would be negative. We can't take ln of a negative number. So this is going to be, if we draw our number line. So here's 3. We're approaching from the right. So say like 3.5. I'm getting close to 3. Well, x squared minus 9, this is approaching 0. So approaching 0. Well, we know, as we approach 0, ln is going to go to negative infinity. So this limit here will be negative infinity. Very good. Next one is saying, take the limit as x goes to 0, natural log of cosine of x. Well, what's the limit as x goes to 0 of cosine of x? Well, what should this be? So as I go here, this is 1, right? If this is like picture of cosine. It's not a picture of cosine, but the general shape, right? As I approach 0 from the left and right. So this is approaching 1. And what's ln of 1? Well, this is going to go to 0. Very good. And one last limit problem I'd like us to do. So we have ln of 1 plus x squared minus ln of 1 plus x. Well, as x goes to infinity, this is going to go to infinity, but this is also going to go to infinity, right? Thinking about this shape. So infinity minus infinity, don't know what that is. So let's do a little bit of manipulation. So this is the limit as x goes to infinity. I'm going to rewrite this as ln of 1 plus x squared divided by 1 plus x. If, I rewrite this just a little bit more, this is ln, equals limit x goes to infinity ln of x squared plus 1 over x plus 1. Now, if we remember back from taking limits of rational functions, well, x squared grows faster than x, so the numerator is kind of dominating this expression. So it's going to infinity faster than the denominator. So numerator wins. This whole term is going to go to, or this kind of ratio is going to go to infinity, so it goes to infinity. Well, ln as x approaches infinity is infinity, so this limit will be infinity. All right, so really quick intro, kind of crash course in logarithms. Let me know if you have any questions or if you'd like me to go through any of this in more depth. For my current Math 265 students, good luck with your studying, and I'll see you all in the next video.